Hello students, welcome back to Math 332 Elementary Linear Algebra. In this video, we are going to look at the concept of orthogonal projections, and also we're going to look at something called the orthogonal decomposition theorem, which we will use it and apply it to show you that the orthogonal complements of a vector space is the vector space itself, which is W perp is equals to W. So just a little bit of warning, this video is going to contain a lot of mathematical arguments, serious types, not a lot of computations. It's more like the mathematical proof and all that. So well, it's going to be a journey. All right, so we are almost done at the end of the semester. This is one of the major tools that we need in order to look at the least square method. So this is the very important concept, actually, orthogonal projections. And let's get right to it. All right, let's look at the objective for this section. So at the end of this video, you should know how to project one vector onto another vector. This is actually something that you should know before this. And the new things that you should know is that instead of projecting onto a vectors, you need to know how to project a vector onto another vector space. So this is going to be something that we're going to talk about. And also you need to understand the new theorem, which is called the orthogonal decomposition theorem, and how to apply them, okay? Okay, let's do a very quick review on a concept that you're supposed to be already familiar with, okay? So suppose we have a vector V and we have a vector U, and imagine that we shine a light right on top of this vector V, and then it will kind of cast a shadow right here. And if you make a vector which is pointing in the direction of U and having this magnitude, all right, having this magnitude, that vector is known as the projections of the vector V onto U. All right, and in order to compute this is actually given by the dot products of U and V divided by this, and then multiply this. So I write so that you will see that this is actually the magnitude of the vector, and this is the direction. Remember, this is still a vector, right? So a vector has two components, the magnitude and the direction. And this is the magnitude, and that's the direction of the vectors. So if you rewrite this, you will see that the formula is given by this, okay? Now, let me make another picture really quickly. Okay, so suppose now I'm going to look at the negative, right? The negative of this vector. So if I put a negative of the projections of V onto U, obviously this new vector here is going to be in the opposite direction of this vectors, right? It's going to be in the opposite direction of this vector and having the same magnitude. I can move this vector up and place it here. Right, this is how we do vectors addition and all that kind of thing in physics, right? So we move this up and right here. So this is the negative of the projection of V onto U. So if we look at what happens when we take the sum of this vector V, right, and then this vector minus the projection of V onto U, what we get is this vector right here, okay? So this vector right here is given as V minus the projections of V onto U. Okay, so this should be clear. Let me make the pictures clearer a little bit. Okay, so we have this now. This is projection of V onto U, and this is V minus the projection of V onto U. And we can verify that by taking the dot product of these two vectors to verify that these two vectors is actually orthogonal to each other. They are perpendicular to each other, and that's the reason why this is also denoted as the perp of V onto U. Okay, just a terminology is instead of keep saying that V minus the projection of V onto U, we're just going to say this is a perp of V onto U, and this is a projection of V onto U. And why do we want to do that? We want to do that because we can write every single vector V as the sum of these projection vectors and another vectors that is orthogonal to the projection vectors. So this picture right here, okay, basically illustrate what happens to this vector V. We can decompose this vector V as the sum of these two vectors which are orthogonal to each other. All right, this is a version of what we call the orthogonal decompositions, right? So we can decompose a vector V into these two parts where these two parts are orthogonal to each other. So these are what this note is trying to tell you, that we can write a vector v onto as a sum of these two vectors which they are perpendicular to each other. Okay, we'll come back and revisit this in a slightly more general context. Okay, so we're going to move on to look at the new concept. So the new concept now is we are not taking a vector and project it into another vector, but instead we want it to project to a vector space. So what does it even mean? How do you take a vector v and then project it onto a vector space? Okay, so we're going to give you the definitions next. Okay, so now we have a vector space W, which is a subspace of Rn, right? So we can't really draw W, but let me draw a cartoon representation. Okay, so let me draw a plane to represent W. Well, sometimes the vector space does looks like a plane, sometimes it doesn't. So especially when we are in dimensions greater than 3, it's very difficult to imagine exactly what happened. But let me draw a plane, okay, to represent this vector space W. And let's this be orthogonal basis, okay, orthogonal basis for W, which means that this U1, U2, all the way to UK, all these vectors not only span the space, span W, that's the meaning of basis. Not only they span W and also linearly independent, we also require they are perpendicular to each other. They are orthogonal to each other. That means that if you take U1 dot U2, right, what is the answer for this? They are 0. Okay, U1 dot U3, what's the answer for this? 0. Right, so as long as your dot products of the two vectors are different, then they will be 0. They are orthogonal. Okay, so if you have this, you have another one, they are orthogonal. If you have this, you have U5, whatever, they are orthogonal. So these are the meaning of orthogonal basis. Right, orthogonal basis. We've seen that before. Okay, so now we have a vector v. Let's say we have a vector v. Right, let's say we have a vector v. And what is the projections of V onto W? Now we can imagine, okay, conceptually, this is not true, right? We can't really draw this, but conceptually, drawing a picture, right? Drawing a picture like this will help you understand this thing a little bit conceptually, okay? So imagine you shine a light on top of it, it's the same as before, then it will cast a shadow, the V will cast a shadow onto W. This shadow right here, this thing right here, this is what we call the projections of V onto W, okay? And how do we compute that? How do we find a formula for this projections? Well, number one, you realize that the projection of V onto W is on W, right? The projection of V onto W is by definition on W. It has to be on the vector space W. And we know that these are the bases. We know that these are the bases for W, right? So these are the bases for W. So if you have a vector that is on W, then it can be written as a linear combinations of these vectors U1, U2, all the way to UK. That's what bases do. They span the space. So if you have a vector that is on W, then you can definitely written it, writing this projection vectors as a linear combinations of U1 all the way to UK. Now, we are going to define, okay? We are going to define the orthogonal projection of V onto W as, which is this one right here, as this. So this is definition, okay? This is a definition. We define the projection of V onto W as this. As you can see, these are linear combinations of the basis vectors right here. Remember, these are not just any basis. These are the orthogonal basis, okay? We'll talk more about that in the next videos. Like, how do we even know there's such a thing as orthogonal basis? We can make orthogonal basis. If you give me any basis, I can remake those bases so that they are orthogonal to each other. That's called the Graham-Smith process. That's a way to do it. So don't worry too much about it right now. Just know that these are not any basis, but orthogonal basis. If that's the case, the projection is given by this, okay? So it's given by this. And we are also going to follow what we did just now, okay? Just now on this, we have another vector, which is called the perp, right? We are going to do the same thing here, exactly following the same way of writing all this perp stuff, which is here. We're going to do that here too. We call the component V orthogonal to W as this vector. So this is perp of V, right? Perp of V onto W. right, is defined as V minus that projections. And what I am going to say is that, okay, what I'm going to say is that this vector right here is actually in the orthogonal complement of W. It's in W perp. Remember what W perp is, right? So you have a vector W. W perp is a collection of all the vectors that is orthogonal to W, right? W perp is a collection of all the vectors that is orthogonal to W, and this is actually an element of it, okay? This is actually an element of it. All right, it's actually pretty easy to see that this vector right here is in W perp. Remember that your W is spanned by all this basis vector U1 all the way to UK. And from before, for prior knowledge, in order to show that an element is in W perp and your W is span of all these vectors, the only thing you need to do is to demonstrate that this vector, the dot product of this vector and this vector is 0, the dot product of this vector and this vector is 0, and the dot product of this vector and this vector is 0, and so on and so forth, right? So let's do that. Let's demonstrate that. It's pretty easy to see that if your vectors V minus projections of V onto W, if you take the dot product with UI, where I is any of this number, then it will be 0, guaranteed 0. Okay, so how do we do that? And this is also where we utilize the facts that all this vector here are orthogonal. These are not just any vectors, these are orthogonal vectors. Okay, so let's see how we use that. So this vectors right here is V minus the projection of V onto W, which is also have another name called the perp, right? Okay, the perp of V onto W. All right, so now let's look at this quantity here, which is actually error is inside this square bracket. All right, now imagine that you take the dot product of UI. I is a fixed number, right? I is a fixed number. We don't know which one yet. It's a fixed number, okay? So it's from 1 to K, one of them, all right? So now once you have this dot product, you can distribute the dot product. You can distribute the dot product, and basically everything will be 0 except for this one. This might not be necessarily 0, but this one right here, if you distribute, right, if your I is not equal to 1, this will be 0 because U1 dot UI, when your I is not equal to 1, that gives you 0. All right, so all this thing here will be 0. The only surviving terms is the UI dot UI terms, right? So UI dot UI will equals to the magnitude of UI square. All right, so this will cancel, and this term here is the same, so it will make a 0. So it's because of that. So we by picking an orthogonal basis, okay, immediately we can see that this particular component, which is this V minus away the projections, is definitely in the orthogonal complement of W. All right, so remember that because we are going to use that. Okay, we're going to use that in a little bit. Okay, we're going to use that, but it's not very difficult to see that this is actually in W perp. All right, in W perp. All right, let's look at one example here. So you have a W in R3. Every time we talk about R3, we are like, you know, it's psychologically easier, right? Because we know what R2 and R3. So let's look at an example in R3, right? So you have equations. This is a plane passes through the origin, and we know that all the x, y, z that satisfy these conditions is actually a vector space. And if we wanted to write down what span the space, right? So you have like something like that. You have a plane. So what actually span this W? Well, the way we do it usually is we solve the equations, find x, y, z. So you can see that x is y minus 2z. These are the two free variables. So we can write it like this. And we know that W is spanned by these two vectors. And actually they are independent. They are not multiple of each other. They are independent. So this form a basis. This is actually a basis for this plane. It's a basis for this plane. No big deal. However, these are not orthogonal vectors. These are non-orthogonal vectors. Look at the dot product of these two vectors, right? So dot product is going to be minus 2 plus 0 plus 1, which is negative 1. So they are not orthogonal to each other. They are bases, but they are not orthogonal to each other. And they are not very good for us in these kind of situations because all our definition of projections, orthogonal projection, and all that, we need a basis that is orthogonal. So we can remake this. Okay, we can reselect a basis that are also spanning the same space and independent and also orthogonal. So I am not going to show you how to do it right now. I'm just going to tell you that we can select this as a basis which is orthogonal. Okay, this is actually another selection of a basis. Instead of this one, we can choose this one. And these are clearly orthogonal. Look at the dot product of these two vectors. This is 0. So, and they actually span the same space. You can kind of see it. You see why? We have this vector. We have this vector. That's fine. And this vector can actually be written as a linear combination of these two vectors right here. They are actually the sum of these two vectors. So I am hand waving a little bit, but if you can write this vector as a linear combination of these two vectors, these two span is actually the same. Okay, so forget about all the details here. If you don't really like it, you can just say that, okay, this one here is orthogonal. Okay, and actually it will also span the same space. All right, so once we have this, okay, we don't want to use this anymore. And once we have this orthogonal basis, okay, we have a better basis now. This is not only just basis, but it's orthogonal basis. Once we have that, we can use the definition to compute the projections. So the projection of V onto W, if you call this U1 and U2, well, that's the computations. So if you compute them, you will see this is what you get. And the perp of V onto W is, again, by definition, this. So you have that. It's not difficult at all. And we can actually look at the picture right here. So this is a W, all right, like a plane. This is a projection of V onto W, kind of like shining a light, okay? Cast a shadow, right? What is that thing? Well, that's a projection. That's what projection means all the time. This is a projection, right? And if you take this, minus away the projections, let me do that again. Right, if you take this vector V minus away this projections, right, vector V, right, plus the negative of the projection vectors. Projection vector is like this, the negative is like that, right? So you add them up, you get this, and we just shown that actually this vector here is orthogonal to actually all the vectors that is from W. So this is actually in W perp. This is actually in W perp. Right, so we can also see that V can be decomposed into the sum of the vector, which is a projection, and these vectors. One of it is in W, one of it is in W perp. So let me say that one more time. This is critical. You can write vector V, okay, as a sum of a vector which is coming from here, from this space W, and another vectors which is from this space W perp. Okay, so that's the example. So all the things that I mentioned here, okay, the vector V can be written as a sum of these two vectors. One of it is from W, another one is from W perp. Is true in general and is given by this theorem. This is called Octagonal Decomposition theorem. So it says that if you have a vector space W, right, subspace of Rn, and if you have a vector V in Rn, that vector V can definitely be written as the sum of two different vectors. One of it is in W and another one is in W perp. And actually, there's only one way to write them, okay? There's a unique way. There's a unique way of writing them. There are unique vectors W from this vector space, and this W, this is just a notation. It's not really perp. It's just a notation to indicate that this vector is coming from this. So this is not the orthogonal subspace. This is a vector, right? This is just a notation that you use in the book. Okay, it's not very nice notation, but immediately it screams that this is something to do with this, right? So that's the reason why the books uses this notation. But I'm saying that any vectors V that is in Rn can be written as a sum of these two vectors. This one is from this W, and this one is from this vector space W perp. Okay, and there's only one way you can write them. It's unique. Okay, that's only one way you can write them. The proof is actually pretty straightforward. So in order to do that, we will have to first make sure that we have a basis that are orthogonal. They are orthogonal bases. We can do that. Don't worry about it. The next video is going to show you how you can always construct a basis that are orthogonal to each other and still span the space. Okay. All right. So we can, for this video, let's just assume that we have that. Okay. We can always get a vector space and then find a basis. Doesn't have to be orthogonal, and then we can run through a process called a Gram-Smith process to find another basis of the same vector space, but this time they are orthogonal bases. Okay, so the proof has two parts, right? First of all, we need to find a vectors W, which is in this space, and another vector W perp that's in this space, so that they will be equals to the V. So you choose a vector V. We want to demonstrate that these two vectors exist. We want to demonstrate, choose a vector V. We want to demonstrate that there is a vector W that is in here and W perp that's in here, so that the sum will be equals to V. And actually the way to do it is easy. We already seen it. We've seen two examples from before already. This W, you want it to be in W. Well, one of the obvious choice is to project the V onto W. So let's find an orthogonal basis, and let's write this vector W as a projection of V onto W. So W perp, let's choose this. Okay, let's choose this. We already know that all the things that looks like this is in W perp, right? So for this vector, let's choose this. And if you look at the sum of these two vectors, obviously it will be V. So V, we found it. It's pretty straightforward. We found V can be written as 1W. One of the vectors, sum of these two vectors, one of them is in this vector space W, and another vector is in this vector space W perp. We did it right here. We did it. That's not a problem at all. Pretty straightforward. Okay. The only thing that is slightly tricky is that how do you know that this is the only way to do it, right? This is the only way to write V as the sum of these two vectors, because the theorem says that there's unique vectors W. How you found it? How do you know this is unique? All right. So the way to do it is the same as before. We assume that we have two different ways of writing them. So suppose we have two different ways of writing it, right? So we have V is W, right? Okay, plus W perp. We already have it. Suppose we have another way of writing it. So let's this one be W1. This is in W. This is also in W. And then we have another W1. This time this is in W perp, right? This is in W perp. So we are basically saying that for this V, there are two different ways of writing it. Okay? You have two different ways of decomposing it into two vectors. One of them is from W, another one is from W perp. And now you want to show that actually W and W1 is actually the same. W perp here and W1 perp here is also the same. This is always the case. When you want to show uniqueness, you show that there are two different ways of writing it, and then at the end you show that that two different ways is actually the same way. Okay, so what happened is, okay, because they are both V, right? So they are both V, so they are both vector V, so they are equal to each other. That's what we have right here. So you move this one to here, you move this one to here, so we have that. And this actually say a lot of stuff. So first of all, okay, W, these are in vector space W, these are in vector space W. So this particular operation here is closure under addition, right? So, and also closure under scalar multiplication for something for the vectors that is in vector space W. So this one here, okay, this element here is in W. W1 minus W is in W. It's in this vector space W. Okay, W perp, this vector space W perp, okay, all right, we show it before. This is also a vector space. So this is one element that is in W perp. This is another element that's in W perp. This is a vector space. So this one right here is in W perp. Okay, so this one right here is in W perp. So this one, okay, this element is simultaneously in W, right? And also simultaneously in W perp. See it? This vector here, right, is in W, but it's also equals to this element, which is in W perp. So this quantity here is simultaneously in W and in W perp. And we know from before there's only one vector that is simultaneously in W and W perp, and that vector is a zero vectors that will give you W1 minus W equal to 0. So your W1 and W is actually the same. So this two quantity is actually the same. All right. So these two vectors right here is actually the same vectors. And same argument, if you look at this, this is in W perp, but also equals to a vector that is in W. So this quantity here is also again in W and in W perp. So because there's only one vector that's in W and W perp, which is a 0 vector, so again, you establish this. So starting by saying that V can be written as this two different way, but now you've shown that this the same. This one right here and this one right here is also the same. So actually, the expression is unique. There's only one way you can do that. The expression is unique. It has to be, this W here has to be the projection of V onto W. Okay, V onto W. And then this one right here must be the V minus the projections of V onto W. Oops, the V is a vector, okay? V onto W. That's only one way to write. That's what we call orthogonal decomposition theorem. Every vectors can be written as a sum of two vectors which are orthogonal to each other, basically, so to speak. Okay? All right, so that's the proof. This is a very nice proof because we managed to utilize the facts that we know from before, which is this. Okay, pretty cool. All right, the last thing we want to do is to apply the orthogonal decomposition theorems to prove this. All right, we used this before. Remember that last time, a while ago, we look at the row space of A, and we look at the null space of A, and we know that the row space of A and the null space of A are orthogonal complement to each other. And I also says that we do this. If we do this, then this is this. And I said that because we have something that looks like this, so this one right here is just this. So we have two way of writing the facts right here. Number one, we can write it like this. Number two, we can write it like this. And I said that it is generally said that the row space of A and the null space of A are orthogonal complement of each other in this manner, orthogonal complement of each other. And when I do that, I'm actually applying this particular theorem right here. And let's look at how this theorem is proved. It's not too difficult, and it is nice to see how we apply the orthogonal complement of the orthogonal decomposition theorem. Okay, so this is two different sets, right? So in order to show that two sets are the same, we'll have to first show that A is subset of B and then B is subset of A. And one side of the inclusion is actually pretty straightforward. So let me just remind you that if you have a vector space S, okay, the orthogonal complements of that vector space S is all the vector V such that V dot S, okay, is equal to 0 for all S that's coming from S, right? So W perp, right, is going to be all the vector V such that V dot I don't know what, let's use W, no, let's use P, whatever, okay, equal to 0 for all P, right, in which one, in W perp, right? Does it follow? Right, so this is kind of like your S, the set S right here, right? This is kind of like a set S right here. Okay, all right, take a look. That's what we have to do. Okay, now, so, okay, I take a vector W. This is a vector W that is from this vector space W. I take another vector. This vector is in W perp, right? So the dot product of these two has to be what? It has to be 0 because that's the definitions of a vector, right? The vector, okay, that is in W perp. Any vector that is in W perp, the dot product with element in W has to be 0. So we have that. And this one right here is actually any elements that is in W perp. This is always true. This is always true for all the X that is in W perp. So look at this. This one right here is kind of like your P right here, isn't it? It's kind of like your P right here, isn't it? So what does it mean? It means that this W is kind of like a V here, isn't it? Right? It's kind of like a V here. It's kind of like the V here. Right? So that means that all the elements in W, right, must be and elements in W perp. This is trivial. This is easy. This is very straightforward. We don't have to use anything special. We just look at the definition of that two sets and we have that, right? So because of this, we have this inclusions pretty easily. We have this inclusion pretty easily. Every element that is in W is actually in W perp. That's the easy part. Easy in the sense that not that, I mean, I'm not trying to demeaning you like you stare at it for like 10 minutes and then you're like, dude, this is not easy. I'm saying easy in the sense that we don't have to use special tool. It's easy in the sense that we don't have to use special tool. We just have to use the definitions and we have this inclusions. Okay. The other inclusion is a little bit tricky in the sense that we have to use a theorem in order to see why the other inclusions is true. And as you can guess, the other inclusions is true because we apply the orthogonal decomposition theorem, which we learn right here. Okay, all right. Looks very innocent, but it is very helpful. Okay, so let's look at that. Okay, so what do we want to show here? We want to show that W perp, right, is subset of W. That means we take an element that is from W perp and show that that element is in W. All right, let's do that. Now, so let's select an element that is from here. Let's call it V, right? So you can see that our V here is in W perp. Now apply the orthogonal decomposition theorems on these vectors. So orthogonal decomposition theorem says that if you have a vector V, if you already pre-select a vector subspace, let's call it W, then we can write V as a sum of these two vectors. This one here is coming from here, and this one right here is coming from here, right? That's the orthogonal decomposition theorem. And also, we have one way to do it. This is the only way to do it. We actually know how to construct this W, okay, and how to construct this. That's only one way to do it. That is coming from the projections, right? So orthogonal projections and all that. So we have seen that from before. Okay, now take this V, okay, and take the dot product. So take the dot product, okay, of this V with this vector here. So take this vector, all right, dot this vector's V and see what happened. So first of all, because this V here, right? So this V here is from W perp, right? That's that V here. That's not any V. This is the V that is from this space. So because of that, because V is from W perp, this dot product here is going to be 0. Okay, this dot product here is going to be 0. So we have that. And because we are taking the dot product, right? So we have taking the dot product, so we can distribute this to this and this to this. So what do we have? Well, so again, all right, after you distribute, this is an element in perp, W perp, this is an element in W. So again, this has to be 0. This has to be 0. And then we have W perp dot W perp. So we have that. So now we have W perp dot W perp equal to 0. We know dot product will not be equal to 0 unless this two vectors is 0. So which means that this vector here is actually a 0 vector. That's the only way the dot product of two vectors is equal to 0. This is again a fact that we know a long time ago. V dot V is always non-negative and V dot V is 0 if and only if the vector V itself is the 0 vectors. So because of this computation right here, we realize that this W perp right here is actually has to be 0. It has the 0 vectors. It has to be 0 vectors, which means that if you select a vector V that is in this space, your vector V is written like this. Okay? It's just V here is just W. It's just W, which is in W, right? Okay? So that's it. If you have a vector that is in here, it must be written as, it must be equals to some vector that is from W. So it is in here. And how do we know that? Because we just computed it. You can see if you start by writing it like this, okay, this part right here is actually 0. Okay, so we have it. So we have it now. Okay, now you might ask, wait a minute, right? You can say that, wait a minute, If you write it like this, okay, then we have that result. What happens if you cannot write it like this? Maybe you have another way of writing it, which will not give you the same result. But that will never happen. That's again, we use the uniqueness. All right, there's only one way to do it. If you really want to write V that is coming as a sum of a vector that's in W and in another one in W perp, this is the only way you can write it. So you don't have to worry about, oh, maybe if you write it like this, we have that result, but maybe if you write it differently, we might not have that result. But we're never able to write it differently. Always going to be just that. So that is the powerful conclusions of that. The orthogonal decompositions is unique. This orthogonal decomposition is unique. Otherwise, we might have some trouble running through this proof. So now we have that established, and everything come back as a full circle. We used that before in the null space and the row space and the orthogonal. We used that before, and now you have seen the proof. And this is no BS. Everything checks out, and everything is cool. Okay, so that's the end of this video. And if you recall, I keep mentioning that we can construct an orthogonal basis for a vector space. So given a vector space, we know how to find a basis for that vector space, but there's no guarantee that that vector space, the basis, is actually orthogonal. So I also mentioned that given any basis for a vector space, even though they are not orthogonal, we can make them orthogonal. So this is a process called Gram-Smith process, which will turn a basis for a vector space into a basis, still a basis, but they are orthogonal. And we're going to look at how we can actually do that in the next video. All right, see you in the next video. Bye.